Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at GlobalFoundries with Dave Eggleston, who's going to talk about next-generation memory and what's coming down the pike in terms of embedded memory. Dave, why are we seeing all these shifts in memory? We're seeing all different types of memory coming to market. People are talking about lots of different options. What's the problem that has to be solved?
Yeah, what we see in embedded memory is a movement towards valuing speed and efficiency. And that's being driven to a large part by the emergence of IoT. We have battery-powered systems that are normally off, and not only do they require good efficiency for power, they also do require some more and more speed. So some new technologies are coming out which assist that move in IoT and that need for power efficiency and speed.
So we've got lots of different choices. How do you determine one versus another? Which one is better? Which one is good for one thing versus another?
It's certainly subjective, and I think that depends on your application. We really emphasize what is the right technology for that application that you're looking at. So in the case of IoT or automotive, which I think are two spaces that are really driving some of these choices, the need is there for versatility. And by versatility, I mean beyond the usual embedded non-volatile memory job of storing code, we also want to start to store data and possibly even state in a non-volatile way, which helps the entire system.
So is this fitting in somewhere between SRAM and DRAM, or is it potentially a replacement for one of those?
Yeah, I don't like the R word of replacement because any new memory technology usually does something particularly well, but it has other drawbacks. But it is definitely between NOR flash or embedded flash, and then also SRAM in embedded systems.
Okay. Why don't you draw this out for us?
Sure. So what we've got is a vector across the bottom, which kind of emphasizes on the far left, data retention. This is the traditional role of such technologies as E-flash. E-flash in the foundry process, in the logic process, has been used for about 25 years. It's going to be used for a long time still because it does that one job really, really well. It stores data in a harsh environment.
Where does it fail?
Yeah, some of the things that eFlash doesn't do particularly well I've listed up here, in particular the write speed. The write speed is very slow compared to other memory technologies which are a little more balanced between their read and write. So as a result, you don't write eFlash very often. Also, its endurance is somewhat limited. It's a technology that tends to wear out. Finally, one of the big difficulties in a logic process is the mask adder. It adds up to another 12 masks, and that can be a pretty big burden on a logic process. Finally, one of the limitations is the analog. The analog required to drive eFlash can be as much as 12 volts or more for that writing voltage. That doesn't scale from generation to generation. So as we get down to 28 nanometer and beyond, eFlash will still be around because of its ability to retain data in a harsh environment, but it becomes an expensive solution and has some shortcomings.
We've been hearing a lot about advanced packaging coming into the market these days, particularly as it gets very expensive to move down into the FinFET world as you need that more versatility and perhaps even more performance and lower power. Where does memory fit into that? What's the best option there?
Sure, so we see more and more requests from customers for us as a foundry to offer some packaging options. So I've listed one up here, which we call SIP Flash, which we see our customers have been doing for a while, and they've started to ask us to pick up and do that and manage the supply chain for them. The real advantage there is now you disaggregate, you decouple the memory process from the logic process. Then a customer can pick, well, what is the absolute best logic process for my application? And then couple that with a certain amount of memory inside the package.
We've seen a lot of homogeneous applications in terms of you've got your logic at one process node, and it was thought initially when system in package was coming out and when we started hearing about 2.5D and fan-outs that we'd be able to put a lot of different things together. We haven't seen that yet. Is that coming? Are you starting to see it?
I think that's coming to a certain extent, that you're going to see 2 die stacks, maybe 3 die stacks. But maybe the dream of putting all these different layers together really hasn't come into being. I think it's because, first of all, cost reasons, and then secondly, one of the key reasons is power. As you need these stronger IOs communicating between dies in the stack, that can consume considerable power. So as systems are more and more constrained by the energy envelope they need to fit into, fully embedded solutions are better for lower power.
And always have been, right? But the downside is that you pay for it in terms of the total cost of development, and you also need a certain volume in order to recoup that.
No question about it. And I think that's where the SIP makes a lot of sense, is to fit some of these areas where time to market may be a requirement that you have, or it could be something where you're iterating quickly. I use the example of the virtual reality or augmented reality headsets. That's probably a place where so much change is going on in a fast iteration that you'd want something like a system in package approach to give you that flexibility. You might want to start off with a larger amount of memory because you don't completely know what your code size is going to be or everything you're going to need for that application. As time goes by, the amount of memory could scale down and you could reach a point where it makes sense to put that on board. So we recommend for customers that are looking at advanced technologies, maybe look at a system in package and look at an external memory and see that as a way eventually to get to the embedded memory space.
And that external memory would be something like HBM2, potentially hybrid memory cube type stuff?
It certainly could be, and at GlobalFoundries we've worked closely on the various DRAM packaging options. In addition, this one is more about using an external NOR flash device. Now that could be used for your code, or that could be used for data logging. It could also be used in the case where you have a base logic chip, and then you start to build out your product portfolio by having different densities, different amounts of memory inside the package. And that way you can get a complete spectrum of the product offerings that you want for your customers.
Process node, substrate, does it matter what you're using here?
It's pretty independent. We're focusing in particular on the 28 and 22 nanometer nodes, but it could be done for any type of node. Particular for 28 and 22, we see a lot of demand from, again, IoT, because this is a place where the market is doing a lot of iterations, making a lot of changes. Embedded memory isn't quite there yet to give the capabilities that customers want, but they want to adopt these new technologies sooner. So we think SIP flash is a pretty good option for those customers.
Is that coming on straight CMOS? Do you see it on FD-SOI? What's it going to be on?
In our case, 28 is definitely on bulk CMOS, and then 22 is on FD-SOI. And below 28 nanometer, we do, at GlobalFoundries, we do see two vectors forward, one being on FD-SOI and the other being on FinFET. And it really depends on your application and your appetite for the heavier design costs for FinFET, which one you will go with.
Is the amount that you have to turn out in volume that much higher out of a FinFET than it is out of an FD-SOI type of implementation?
So I think development costs on FinFET are definitely steeper. So you have to look at high volume opportunities like processors, and we do ARM processors, by86 processors, and power processors, all of which are done on FinFET. So that vector is really where you want performance, performance, performance. FD-SOI is a little more reasonable offering for a lot of different applications where you don't need the performance, you may not want that design complexity, and you may want the lower power, the energy efficiency that you get from FD-SOI.
So what do you see for the FinFET and FD-SOI generations as we're going forward? We've been hearing a lot about the new memories. What's coming?
Yeah, and that's where we have a number of choices to make. So let me list some of those memory types up here, and then we'll talk about each one individually. So the first one would be embedded MRAM. And then there could be embedded RRAM. You could have phase change memory, or we've also seen in some cases carbon nanotube. So each of these four have their own pluses and minuses. Embedded MRAM I'm going to talk about first. Embedded MRAM, if we're going to sum it up in one word, I think it's versatile. And we emphasize the versatility of embedded MRAM because through both design and process, we can utilize the technology and tailor it to the needs of the application. That might be for data retention, or that might be for speed.
We've been hearing about MRAM as eventually a possible universal RAM. Is that likely, or are we still going to be a variety of different memories all the way scattered around?
There's going to be a variety of different memories. We're in an SRAM, DRAM, NAND world today. What we're talking about here is MRAM specifically for the embedded market. It does certain jobs well, but it certainly will not cover all the tasks of all memory types.
Where does it fall down?
Yeah, I think where embedded MRAM has some negatives about it, it is a complex device to process. So between the two electrodes, when we form the storage element, there's a number of different atoms and a number of different layers involved. That does require specialized equipment and a lot of know-how on how to bring that into the process.
There's been a lot of talk about MRAM for quite some time. We've yet to see it really roll out in the marketplace. Is it coming for sure, and when do we expect to see it?
Yeah, so from our partner, Everspin, Everspin has shipped MRAM for a number of years, including they're starting to sample product built at GlobalFoundries. Looking at the wider foundry community, besides ourselves, we're aware of two other foundries that are developing embedded MRAM for the 28 or 22 nanometer nodes. And then also there is one of the largest processor makers who's invested heavily in MRAM for their own purposes. So we do think that the foundry community has spoken, certainly from advanced foundries. Now that does take a big investment. It's several $100 million to go invest in this new technology. So we don't expect that is going to be across all foundries worldwide, but only those that can bear that heavy burden of R&D expense.
And the chief rival to that is RRAM, right?
RRAM is in some ways a rival to MRAM, but I think where RRAM falls a little bit short is we think it's somewhat limited. We think RRAM is somewhat limited in that its endurance is not as high as MRAM, certainly, and then its write speed is also not as fast as MRAM. So it lacks that versatility to get into the working memory space where SRAM currently resides.
How about phase change memory? We've been hearing about that for a number of years too.
Yeah, I think phase change memory does seem to have a particular role. So phase change memory is primarily being used as 3D crosspoint, which I do consider a variant of phase change memory. That's being done by Intel and Micron specifically for the server memory business. So we do think that there could be an application there, but that's more as a standalone memory as Intel and Micron is introducing it. Not that relevant to embedded memory for foundry.
And the other entry in this carbon nanotubes, we've been hearing rumblings about carbon nanotubes going on about the past decade, yet to see them actually come into commercial use.
Yeah, I think carbon nanotube may have some promise, but it does seem to be very immature. So I think if I were to sum that up, that's the possibility here, is that over time, especially if we see carbon nanotubes come into play for very small geometry, single-digit nanometer type transistors themselves, if the technology comes in a bigger way into the fab, could it also be used for memory? I think there's that possibility, but that's still probably 10 years or farther out.
Okay, so if you're an architect designing a system here, what do you need to look at in terms of, okay, do I want to go MRAM, do I want to go RRAM? There's a lot of different possibilities out there.
Yeah, and again, I think I come back to, in our case, we would emphasize that with MRAM, you have the versatility. And what I mean by that is if you want to have code storage on board the chip, and that's to do the same function that you might have used eFlash, once you've made that investment, could you do something in addition to that? So let me draw up here a situation where, let's say you're using a block of eMRAM for your code. And you may have clustered a number of processing units around that. So this would be multi-cores. These could be CPUs. You could have a GPU. You could have what we call a VPU, a vision processing unit. So the question is, if I've invested in putting magnetics on my wafer, what else can I do? what we see customers asking for is, well, now how can I also use eMRAM to do more of a working data function? So this would be your data and your state. Now you don't get rid of SRAM, but you might reduce the amount of SRAM you have on board. So the SRAM and the eMRAM work together. I generally call this type of eMRAM-S for SRAM-like, and this type of eMRAM-F for flash-like.
And one of the things that we're getting into when we get into the automotive market, which you were talking about before, is the need for really good reliability. This stuff has to last. Unlike a mobile device, it has to be around for 7-10 years minimum. Which one of these works best?
Yeah, so eFlash is the champion technology when it comes to retention in a harsh environment. No question about it. That's why I still say that eFlash will be around for a very long time. But for the automotive market, one of the places we see a driving application is with autonomous vehicles. With autonomous vehicles, what you're doing is you're pulling in a 3D map, probably from an SSD, and then you're hashing that with what your vision and LiDAR systems are telling you are going on around the vehicle. So the ability to just have more memory, more working memory to do that vision processing is a key thing. So as we think about these applications, pushing us away from the left side of my vector over here, which was data retention, more and more towards speed, you need a new technology. And that's where we think the versatile nature of eMRAM makes a lot of sense.
These are particularly harsh environments as well. Will all of these function well in a very harsh environment, high heat, extreme cold?
I think all the new memory types are challenged. How well are you going to survive that harsh environment? We've done a lot of work to harden our eMRAM technology to make sure it works in the harsh environment. One of the advantages that MRAM does have in those harsh environments is still it has a native, much higher endurance than other technologies. So we are working with the automotive electronics makers to even look at doing an occasional system data refresh, which would get around some of those issues. Plus, it would give the opportunity that on every key twist or occasionally, you could update the code in the microcontrollers that you have around a car.
As we move down each node, one of the issues that a lot of people have talked about is process variability. Does that affect any of these memory types as we push down?
I think it affects all memory types because memory, especially non-volatile memory, is a statistics game. Can you get enough bits to work most of the time? There's no question it is a challenge for all these memories as they scale down. I don't think any one of these has a unique advantage over the other. I think the cell-to-cell variability is there, and one of the things, all memories will require some amount of error correction. They will not be perfect memories, and we'll need to work around those occasional bits that fail to write or bits that lose their data on the read.
As these memory types begin rolling out in volume, are we going to see much difference in terms of pricing and difficulty in working with them, or does everything get smoothed out as it has with Moore's Law?
Yeah, I think that's a great question because there is some initial R&D investment, and depending on the unique CapEx that you have to bring into the fab, that does have to be paid down. I think we're working in a certain envelope here. I think that envelope is the technology has to be competitive versus eFlash, and it has to be, even from the beginning, has to be priced at parity or slightly lower than eFlash. But I think one of the main advantage for all of these technologies, they're considered back-end of line technologies. So the number of masking steps is less. So what I call steady state, which is after you've paid off the initial R&D, that initial CapEx, then we should see considerable price declines relative to eFlash. It's going to decline faster than the underlying platform declines.
And for each one of these, is there a big difference in terms of performance and also power?
There is a difference for each of these. And I think that that's one of the drawbacks for embedded MRAM is it does take quite a lot of power to switch. And certainly RRAM can also take quite a lot of power to switch, although to a lesser degree. But on the flip side of that, from MRAM you get native speed for write, and then you also get endurance. So it really is understanding your application, understanding what is the right technology. And again, from the foundry point of view, the investment to get into each of these technologies is pretty large. So we have to make sure that we can utilize this technology across a broad space of applications to recover our investment.
Dave Eggleston, thanks very much for a great explanation.
Thanks. It's been my pleasure to talk about next generation memory.